Professor Sills here with your Chapter 12 wrap-up, and just want to share a few thoughts with you as we go through this so you have a better understanding of what's really happening here. You know, if you think about the atmosphere, you have polar regions which never received enough energy, and tropical regions which always receive too much energy, with the 37th parallel, roughly Washington, D.C.'s latitude, being the demarcation line between a deficiency of net radiation year-round and an excess of net radiation year-round further towards the equator. Now, what that does is it means if there was not some other method of exchanging energy, you'd always have the tropics heating up year over year over year, and the poles would be cooling off year over year over year. The great equalizer is convection, and that is the flow of a fluid. That would be, of course, water and air. And with respect to the atmosphere, since you have a pool of warm air building up over the tropics, specifically, look at the Gulf of Mexico in the United States, and something important has to be pointed out here. The United States, North America, is the only major landmass that does not have an east-west mountain range which separates the Arctic, if you will, from the subtropics. For example, over in Europe, southern Italy and Spain and the French Riviera are rarely subjected to Arctic outbreaks, even though they're not that far south, because you have an east-west mountain range which is blocking the Arctic air further north from working its way southward. Here in the United States, we have no such boundary, which means that warm, humid air over the Gulf can advect or convect northward towards the mid-latitudes, and of course Arctic air can advect southward from Canada and across the United States. And that's how you can get the kind of temperature contrasts that occur. It's not unusual in March at all, and we saw it this year, where you have a day or two where it's in the 70s, mid to upper 70s, and then you have a day or two where shortly afterwards it gets much colder and even snows. So that's not an unusual circumstance. So here's the thing to understand though. The atmosphere is inherently unstable. What you're looking at on stage one here is not a stable situation. You're not going to have warm air just stay where it is to the south and cold air stay where it is to the north. There's always going to be a little bit of a push, and that's because the winds, the upper level winds, are dynamic. So when that push occurs, you're going to see, if this thing cooperates, you're going to see the, let's see if I can drag it along. Well, maybe it doesn't want to cooperate. In any case, you're going to see a wave cyclone pattern with the warm air pushing northward, the cold air pushing southward, and you form a warm front and a cold front, much like this. I'm trying to do it so it looks right. Is that right? Anyway, something like this. Boy, does it. Like that. That's all right. Forget about it. You can see it on the maps. It's detailed on the maps in the book. In fact, I'm going to pause this. I'm going to find the right map so you don't get confused. Okay, so I went over to a different graphic. So here we have the initial stationary front stage, cold high to the north, a warm high to the south. In other words, continental polar or Arctic air to the north, maritime tropical air usually to the south. That's typical of the setup, especially in the United States. As the cold high begins to push southward and the warm high begins to push northward, you begin to get two frontal waves. You have the warm front and you have the cold front, and they're well separated. You have, if you look at a cross section, here's your warm sector right here. This is your maritime tropical air. Here's your cold sector back here. That's your continental polar air, separated by the front. Here's your front, vertically developed. Here is your cold front. Here's your warm front over a long sloping surface, and here is the warm front at the surface, sloping upward as it reaches to the north. That's why there's a long plume of clouds ahead of the warm front as it approaches you. And again, up here, you're also in continental polar air. Might be modified continental polar air, but it's continental polar air, and that's what's labeled as section C to D, that would be C here up to D here, let's say. Now, over time, because cold air is denser and warm air is less dense, cold air is denser, warm air is less dense, the cold front is able to make better forward progress into the warm air than the warm air is against the cold air. So in English, the cold front moves faster. So what happens? If we go to the next slide here, the cold front eventually catches the warm front, and what you have is an occlusion. Now, looks like we have an animated profile. And here we go. So as the cold front catches the warm air is pushed aloft, which forces it to cool anyway. And what set the whole thing up in the fact that there was a temperature contrast, warm air to the south and cold air to the north, gone, and therefore the system dissipates. That's why cyclones have a life cycle and they last maybe for a week or so. Or 2 weeks at the most. So let's go forward with this and take a look at the additional questions. Number 10, I've got a slide which should illustrate this nicely. For number 10, the question is necessary ingredients for a mid-latitude cyclonic storm to develop a huge storm system. Cape Hatteras is the most perfect place for developing storm systems. Why? Because Cape Hatteras, right here, eastern tip of North Carolina, has immediately off the coast the Gulf Stream. The Gulf Stream is a stream of warm water that originates in the Gulf of Mexico and works its way northward along the Atlantic seaboard before turning out to sea this way towards Europe. Well, that Gulf Stream brings extremely warm water all winter long, very close to the coast. When I say extremely warm, you go 20 miles off, 50 miles off the coast of Cape Hatteras, and the water temperature is in the 70s even in January. That's going to warm the air above it. So it creates warm air aloft, offshore. Meanwhile, Arctic air and continental polar air work their way down across the mainland. You might recall that was one of the main problems that the settlers first had when they reached Virginia. They were from originally over in Europe, where they didn't get cold in Spain and Portugal in the winter, but here, because the Arctic air comes, I'll draw it in that way. I've got to remember that. I've got to go backwards. Anyway, I'll do it this way. It comes in here and works its way southeastward. So that cold air doesn't modify until it hits the coast. Well, when you have temperatures in the teens and 20s in Virginia and in the Carolinas, especially North Carolina, which is not unusual in December, January, and February, and then just off the coast you've got much warmer air because of the warm water underlying it, that creates what we call a baroclinic zone. In other words, a major thermocline, a major boundary in temperature between just inland and just off the coast. That is one of the major ingredients. Combine that with a jet stream, that means a streak of air running its way up the eastern seaboard, and anything that develops here is going to race north and eastward, and certainly in New Jersey that happened often enough this winter. And as long as it stays to the east of, let's say, Patterson, then the circulation around this thing is counterclockwise, and that means that the air over on the inland side is blowing from the northeast. Hence the name nor'easter. That's where Ben Franklin got it from. He didn't understand how these things traveled, the fact that they travel towards the northeast. What he understood is the wind was blowing from the northeast. Well, a northeast wind in New Jersey, just put an arrow here, a northeast wind in New Jersey is coming from Connecticut and New England, northern New England. That's cold air, and that allows for all the snow to occur even into March and April when you get those northeasterly winds. So that kind of summarizes everything you need. Looking at question 14, why surface high pressure area over North Dakota typically moves southeastward? The answer is relatively simple. The jet stream is carrying things, primarily weather systems, I shouldn't say things, carrying weather systems, highs and lows, from west to east. You see one here migrating eastward as we are approaching the 26th of March, 2011. So, and this system, by the way, is actually going to bring some lousy weather, potentially to New Jersey, but definitely south and east, and it may even include some snow in South Jersey or even in the Delmarva Peninsula area. As this thing works its way eastward, it's still cold enough. Sources of energy for developing Cyclone 15, that's your warm air to the south and your cold air to the north. It's the temperature contrast which will do it every time in the winter. Okay, question 1. British friend of yours says last night's rain over the northern coast of Great Britain was caused by a storm that originated east of the Colorado Rockies. Well, simply enough, a storm system that originates here, east of the Colorado Rockies, will be carried by the westerlies. Westerlies are global winds. They don't stop on our east coast. They simply continue east into the Atlantic. And if I could draw this, and if we were able to continue over to Europe, whatever is traveling across the U.S. will eventually work its way over to Europe, which is the same reason that what happened in Japan worked its way over to the west coast of the U.S. And that's why some people on the west coast of the U.S. in March of 2011, for those who are seeing this much later, were a little concerned about radiation reaching our coast. History has shown that very little radiation reached the coast, and all those people running out for gas masks simply lightened their credit cards for the month. Anyway, Professor Sills signing out. That'll take care of Chapter 12 for you.